And now for a slightly different question again, we want to look at our n cubed graph here, Qn, and decide for which choices of n is this graph going to be planar. And we're going to start by using this rule here, exactly what we did in our previous question, to rule out some cases. Because as we found out with G2 previously, we can't use this to verify whether a graph is planar, but we can certainly use it to verify that a graph is non-planar. So we just recall that if G is connected, simple and planar, and has no circuits of length 3, then we have twice the number of vertices minus 4 is greater than or equal to the number of edges. And I'm using this one because I know my n cubed graph has no circuits of odd length, so I can definitely use this for any choice of n. And further, we want to recall that Qn has 2 to the n vertices and n times 2 to the n minus 1 edges, right? So that tells us what our v and e are here. So for any n, looking at my left-hand side there, I get 2v minus 4. Well, that's going to be 2 times 2 to the n minus 4. And I can probably rewrite that as 2 to the n plus 1 minus 4. And e, well, down here we can see e is just n times 2 to the n minus 1. So just comparing these two, I can see that I've got n times 2 to the n minus 1 and 2 to the n plus 1. So maybe something is going to go wrong with my inequality if this n is big enough to make this greater than this. And so let's see what happens. If n is greater than or equal to 4, so 4 is 2 squared, that's going to carry me from 2 to the n minus 1 to 2 to the n plus 1. I'm going to get n times 2 to the n minus 1, which is certainly going to be greater than or equal to 4 times 2 to the n minus 1, which is going to be strictly greater than 4 times 2 to the n minus 1 minus 4, because I'm reducing something that's already positive, and that is 2 to the n plus 1 minus 4, which is exactly 2v minus 4. And so I can say, well, since this inequality here tells me that this inequality fails, something over here must go wrong, and we know all of our QNs are connected, they're simple, and as I said before, have no circuits of length 3. So the thing that must fail is that our graph is planar. So Qn is not planar when n is greater than or equal to 4. But what happens when n is less than 4? Well, the only thing we can do is actually try and draw some planar representations, see what goes wrong. So let's have a look at that. Okay, so the easiest way to show that a graph is planar is actually by drawing a planar representation of that graph. So when n equals 1, Q1 here, that's just 2 vertices joined by a single edge, very obviously planar. Good, done. When n equals 2, well, Q2, that's going to be 2 copies of Q1 with corresponding vertices joined together. So I've got my 2 copies here and here, and I join their corresponding vertices. This is obviously planar. Q3, take 2 squares and I join them together by their corresponding vertices. And I look at that, this is not planar. But this is not the only way to connect 2 copies of Q2, so 2 squares. Another way I could do this is by taking 1 square and then putting another one outside. And then I take each of these corresponding vertices and I connect them. Right? So we can see, just by stretching out this back square, I can get this version of my graph. So we can see that these two are isomorphic. And so hence we can say Q3 is planar also. And that covers all possibilities because, as we said before, for Q4 or anything greater, it's not planar, which we used our inequality for.